So let's take a look at this problem. So we have a linear transformation that rotates points through an angle of 3 pi over 2 radians. By the way, how many degrees is 3 pi over 2 radians? 270. So we just want a matrix that rotates points through an angle of 270 degrees counterclockwise. So what's the protocol here? How do we find the matrix, the standard matrix, that represents a given linear transformation? What do we have to calculate in order to make that happen? Yeah, if you like memorizing, then every rotation matrix has that form, cosine minus sine, sine cosine. I want to take the more sort of general view of this that can help you find the standard matrix for any linear transformation, not just for a rotation. How did we do it? We took the standard basis vectors 1, 0, and 0, 1. So here's 1, 0, and here's 0, 1. And then we just applied this transformation to those standard basis vectors. So if I take the vector 1, 0, and I do this to it, where does it go? If I rotate it 270 degrees counterclockwise about the origin. Where does it end up? (270 degrees being 3 right angles. Right? If we start on the positive x-axis and go 270 degrees counterclockwise, we end up on the negative y-axis. What vector describes where it lands? Zero, negative 1. Yeah. So I'm going to paste this over here. There we go. So the image of the vector 1, 0 under this linear transformation is 0, negative 1. So just to organize what we have here, t applied to the vector 1, 0 is equal to 0, negative 1. And so what do we do with that piece of information? If we know what the image of the first standard basis vector is under this linear transformation, then where does that go in my final answer, i.e. the matrix of this linear transformation? What do I do with that information? So 0, negative 1 is a part of my answer. Which part? So I'm going to actually... right there. It's the first column because it's the first standard basis vector. So this, by the way, already kind of indicates to us that the same linear transformation can have different matrices associated with it if we make different choices. And one of the choices we make when we produce a standard matrix is we choose the first column of the standard matrix to be the image of 1, 0, and the second column to be the image of 0, 1. So we're kind of already being a little bit arbitrary about this, that we want to look at the image of the purple vector here first and then the green vector second. If we did those in the opposite order, then the order of the columns of our matrix would be flip-flopped. But when we say standard matrix, not only are the vectors themselves that we're using to do this standardized, but so is the order in which we place those vectors' images is also part of that standard word in a standard matrix. So the first column in the matrix is just exactly t applied to the first standard basis vector, 1, 0. So what does that make the second column? Where 1, 0. It's where 0, 1 goes, the second standard basis vector, if we rotate it by 270 degrees And sure enough, it does land on the positive x-axis. Specifically, it lands on the vector 1, 0. And so the second column in the matrix A is 1, 0. And again, I like this method of coming up with a standard matrix as opposed to, always trying to memorize the form of a bunch of different kinds of standard matrices. Just because this method now will work for any linear transformation. All I have to know is what happens to the vector 1, 0, that becomes the first column, and what happens to the vector 0, 1, that becomes the second column. And then as soon as we have those two columns, we have our answer. Here's a standard matrix of A. So going from a linear transformation to a matrix is a bit of an art, but if we're talking about a standard matrix, all we have to know, because of linearity, as soon as I know how to transform 1, 0 and 0, 1, then secretly I know how to transform every other vector in the plane, because I can write every other vector in the plane as a linear combination of these two standard vectors. That's why this matrix, which has only 4 numbers in it, is capable of describing what happens to the entire xy plane under this linear transformation, because everything depends on what happens to these two standard basis vectors. So just take the standard basis vectors, transform them, and that's the fun part, because you have to read through the transformation and figure out exactly what it's doing. And then the transformed images of those standard basis vectors are the columns of the standard matrix.